Uh, all right, guys. So good afternoon. Let's uh, let's uh, let's start. So before a couple of classes back, we have seen. So what did we do? We started with this thing that so we have to read a list of names and sort the list of names. Um, so we kind of went into multiple things. So first is we started with the static array, something like, so what did we do? So we have something like char star names. And then so we use something here. The problem with this approach is you can only accommodate 100 names. So if there are more than 100 names, then this doesn't work. And if the number of names is way too less than 100, then the memory wastage is there. And then, so how did we solve this problem? The way we solved this problem is we used dynamic memory. We used malloc, and we initially started with, so we used something like this. We used char star star names. And then initially we started with some initial size. malloc, let's say initial size is 100. And when it is full, we used realloc to expand from 100 to 150. And again, if we are full, we use realloc from 150 to 200, like that. So yeah, the problem in this is kind of all right approach, but the problem is when we are moving from malloc to when we are trying to increase the size of the uh, array, there is a lot of copying that is happening because like when we try to use realloc, the malloc library tries to see if it can expand the memory that is allocated previously so that it can avoid copying. But if it is not possible, it will try to find an empty chunk of memory in the heap and copy the whole stuff there. So that's the problem with this approach. And also issues like what should be the increment value, what should be the initial size of the array. All these questions are there. So one way of solving this problem is by using what are called as linked lists. So what we do is, let's say you read a name and store that name in one record, and then let's say if you have one more name, what you do is you get one more record from the memory, and then you make this the head of this is the first structure in the linked list, and it will point to the next. And then you read one more name, and then you figure out, you know what, I have one more thing to handle. So you kind of uh, allocate one more structure and make this point to this. So like this, it keeps going. The advantage with this approach is at any point in time, you don't need to know. So you just dynamically grow, completely dynamically grow. So if you don't want this record, you can kind of, let's say you want to delete this record, you can free this memory space and then make this point to this, like this. So there are two things here. Let's try to get this code right. And then, so this, yeah, so let's try to get this code right. And then after that, we will see what are the advantages and disadvantages. So let's get the code going. So you have Control N, new file. So yesterday we were looking at, yeah, so let's start from the scratch. So time now is 2:10. Let's see if we can finish it, how fast we can finish it. So I just use this, let me use this thing, linker list, list.c. Main. So let's say what we do is we kind of read a list of so this is the way we are going to define our structure. So we have what is called as a node, type def struct node. Let's say we are holding integers. This is the marks, okay, in each or why just roll number. I don't like marks, so let's have roll number. And then, so what we do is we have one more thing, struct node star next. So are you with me on this definition? So this is an interesting thing. So this node, it contains two fields. One is the roll number, and it contains a pointer which points to the next structure. Yeah, so I want you to pay attention on line 5. This is the tricky part, okay? Because we are using struct node within struct node, and it is permitted in C. When you are looking it for the first time, this is what would be confusing. What if we replace this with node next? I think this wouldn't work. It's a good question. I also thought about it, but I think it wouldn't work. Oh, it's working so far. Yeah, it's working. So good idea only. So good question. So are you all with me in the definition? This doesn't work. Huh? Let me compile this code and see what happens. I just thought that, no, why not give it a try? GCC this.c. Okay. There is an error. So there is an error here. So because of that, but this should work. Yeah. Are you all with me here so far? The only key thing that you should understand here is on line 5, we are permitted to use struct node within the definition of struct node. So that is the only tricky part. Otherwise, it's all good. Right? So what do we do? So what we want to do is, so let's say, so we want to read while scanf %d /n. So we want to maintain a linked list. We want to maintain a linked list. So we will say node star head. Okay, so head points to, we will have a list of nodes, and those nodes are linked with each other, and head will be the first one. So node star node is equal to, yeah, let me use a global variable so that in order to make your life easy. Otherwise, you'll have pointers to pointers to pointers like that. Node star. So initially the list is empty. When we start the program, please pay attention. And when we start the program, no, that head is a global variable. Head is a global variables, and we are using the type of the node is capital node, NODE, right? So because of that, we use capital node star head. And on line 14, we have head is equal to null because initially the linked list is equal to null. And what we are doing is we are reading one int roll number. So we are reading one roll number at a time, and so int roll number so is not equal to end of file. So what do we do? So create node. So all I am doing is now, so insert, what do I do? Yeah, let me do this thing. So current node C node is equal to create node roll number. Can someone tell how we go ahead and write the code for all right, C node. So we want to write a function called C node, node star, create a node, and it takes a roll number in it. And what will it do? It will create a yeah, node star. T node stands for temp node, and you create T node is equal to node star malloc size of node. So we are creating memory which is equivalent to so we are creating memory. We are creating memory equivalent to one node, and what we are doing is we are setting T node roll number is equal to roll number. Great. And the other thing we also do is T node next is equal to null. This is how we are creating. Are you all with me on line 11, the create node function? I hope you are all with me in the create node function. Great. So now what we create a node, and then we want to insert this node into a list. Insert node. What do I do? C node. No. When we do node start T node on line 13, memory will not be allocated. We have to. So that is a pointer. T node is a pointer. Very good question. Kush has a very good question. So T node is a pointer variable. So like for example, the size of the structure, let's say a pointer variable is allocated 8 bytes. The pointer variable is allocated 8 bytes, for example. Uh, so the size of the structure, it could be anything. Like for example, here on line 15, what is happening is, so let's say somewhere in the heap memory, let's say this malloc returns somewhere in the heap. So where the size of this memory is equal to the size of the node, and the base address of this will be allocated to T node. So the size of this node can be 8 bytes, 16 bytes, 20 bytes, it doesn't matter. But the memory that is allocated to T node will be somewhere here, it will be fixed. It will point to the base address of this memory that is coming from the heap. Does it make sense, Kush? And the second important thing is, where is the memory for T node allocated? Where is the memory for T node allocated? In the stack, guys, in the stack. T node is a local variable. T node is a local variable. So when we call, so when main calls, so this is main. So when main calls create node, so this is important. So if you look at the stack, so this is the activation record for main. This is the activation record for main, and this is the activation record for CN. CN is create node. So memory for T node will be allocated here. This is T node, for example. But the memory that we obtain through malloc, it is coming from heap. At the end of on line 19, what happens is after line 19, the address of the memory in the heap is returned, but the memory that is allocated to T node, which is on the stack, gets released. Are you all with me here? How many of you are with me here? T node is a local variable and it is allocated memory on the stack. But when we do malloc, the memory is coming from the heap. And the memory that is coming from the heap, it will not be released until we make an explicit free call. Yes, T node is in the stack and it is pointing to the memory in the heap. And the memory that is allocated in the heap via malloc, it will not be released unless we make a call to free function or the programmers, of course. Yeah, so when we come out of T node, create node, the memory of a T node is freed because T node is allocated memory in the stack, in the activation record. Are you all with me here? The T node is on the stack, and the memory that is allocated to T node will be released after we come out of create node function. And malloc, when we do the memory that is allocated using malloc, it comes from the heap. Okay. And it will not be freed until we call the free function. The code is not yet complete. We are trying to do stuff here. So all right. So now we have to write one more function, insert node. So void insert node node star C node. So here initially what we do is so we check if head is equal to. So we are using one global variable head. So we check if the list is empty. If head is equal to null, what should we do? So initially when we started, if head is equal to null, then when we insert a node into the list, so yeah, we should do head. If head is equal to null, initially there is no element in the list, then we just put that element in the list. So in which case we say head is equal to C node. So here, so initially this is there is no list. So when you call insert node, so then what happens is, so this is the only node that is present, and so head is somewhere here. No, head is initially null. Head is initially null. So now it will point to, let's say you have inserted an element with a node with roll number 12. All right. So now what happens is head will point to this. and this will be a null pointer. This will be a null pointer. So let me use a different notation for null. Okay, so whatever. Null pointer means null is 0 actually. It's, so when a pointer is not pointing to anything, you just make it equal to 0. But on the contrary, let's say you want to, the current state of the list is already, and if you want to insert 13 into this list. So what should we do? Can someone write the code for, show me the code? This is the current state of the list. This is the current state of the list. There is one element already present, and we want to insert this element into the list. What should we do? Let's say we want to insert it at the front. So there is this next variable, right? So this one should point to this, and this should point to this. So how do we make this point to this node point to this? The way we do it is C node next is equal to head. C node next is equal to head, and then head is equal to C node. That's it. Are you all with me here on the insert node function? Yes or no? I hope you're all with me here. No, Kush, it's not node star star C node. We can have head next is equal to C node, or we can just have head is equal to C node. Both will work fine. Maybe. Interesting question. The most interesting question is from Kush. That is, shouldn't we have node star star C node? So it's not the case. We don't. Yeah. So what we are doing here is, so initially the list is empty, and initially the list is empty, and let's say, so you create a node with value 12 in it, and head initially is the initial state. Let's say state S naught, head is equal to null. This is the uh, first state, and then we have S1. S1 is the state when we insert 12 into a node which contains 12 in it. Let's say the base address of this node is 100. So now head contains 100. Head is equal to 100. Head contains 100, the base address. That's what we are doing here. That's what we are doing here. So when we are passing C node here, we are passing 100 here because we are passing the base address of the node. Are you with me here? Till state S1, what is happening? Are you with me on till state S1? And this value is null. Null is equal to 0. So let me put a 0 here. So let me put a Uh, Let me use a capital N to indicate it is null. Are you all with me till this point? I want Kush to check. Kush, are you with me here? Because this till this point we are passing 100 here. 100 is the base address of this structure. And that's what we are pointing. And head, head I made it a global variable so that we don't get into passing pointer to of head and all, so that one less headache for you. So now when we are trying to insert a node 13, so let's say the address of that node 13. So the address of node 13 is this is 12, this is null, and let's say we got another node whose address is 200 and that contains no, let's say 20 in it. And this is when we made a call to create node, this is the node that is given by the create node function. Are you with me here? This is the node that is given by the create node function. And so head is equal to 100. So head is equal to, let's say this is the memory for head. This is the memory for head, and head contains 100. So what should we do? Let's say if you want to insert this node at the beginning of this list, there are two things that we should do. Number one, we should make this node, second node, point to this. How can we make the second node point to this? By making this contain 100. And how do we get this? We make C node next is equal to head, because head is contains this the current head, right? And what is the second thing that we are doing? We want to make head point to this. And the way we do it is we just C node contains, remember now C node contains 200, not 100, because 200 is the base address. So what we do is we make head is equal to C node. So because of that, what happens is here we will have 200. We should not think of it that way, that we are inserting an element between head and we are just inserting an element at the beginning of a node at the beginning of the list, and head always we need to have a handle for at least one element of the list to traverse the list, right? And that's what head is doing. It is providing us access to the or the address of the first element in the list. Yeah, that's true. So as we keep adding, this is the state S2. And if you want to add one more node, let's say whose address is 300, let's say we want to add one more node, let's say it contains 30. And so this is what is given by the create node. And let's say it is 300. What do we do? So the way we do it is, this is what, so this should point to this and this should point to this. And this pointing to this is nothing but, so you should put 200 because 200 is the address of this, and no, and head should contain now 300. So Kush, don't get stuck there. I will explain what is happening here. So like C node contains the base address. Like for example, here C node in the third case we are passing 300. So the good part is when you know the base address 300 and next is like for example, if you do 300 plus 4, you get the address of C node next, because we have the first variable in the node is a roll number and it just requires 4 bytes. So when for C node next, we know how to compute the address and then do the necessary modification. Or if it is C node roll number, like for example here, let's say when T node, when malloc returns 300, when malloc returns 300, when you say T node roll number, this internally gets translated to 300 plus 0 star. 300 is the base address of the node and 0 is the relative offset of the roll number field within that structure. And this one gets translated to star 300 plus 4, because 4 is the relative offset of the next variable within that structure. Does it make sense, guys? Are you all with me here? So because we know the address of it, yeah. Okay, so now, so I'm clearing this picture. I hope you got a decent idea. Clear all my drawings. So now let's say what we did. So this is what we did. We just created a list of nodes. So and after that, let's say all the things that is there in the list, let's say we want to print. So printf list of roll numbers. List of roll numbers we'll have slash n. Let's say I will have print list function. So can you go ahead and write code for the print list function based on, can you mentally think of how you can write the print list function? Recursively, good. So, but let's use iteration here. So we will use a for loop. So we use what is called as a C node. Current C node is equal to head. C node not equal to null. What do we do? Yeah, we'll come there in a moment. So we will say printf %d /n C node roll number. And after we print the current roll number, so what do we do? C node is equal to C node next. Are you all with me here? Does this code make sense? You keep traversing and finally you, when the list gets exhausted, the C node becomes null. Okay, this is print list. Why is it still giving a problem? Okay. So now let's compile this code. Let's see what happens. GCC list dot C malloc hash include malloc dot h. Yeah, vi roll number dot text. So let's say 2020, 123, 2020, 124, 2020. Hey, what happened? Something interesting happened with my VI editor. Do you think I'll get a segmentation fault? No, I'm not getting any segmentation fault. So that's all. So are you all with me here on this? If you have to write a search node function, what do you do? How do you do if you do a search node function? You traverse and at every point you check if that if that is present or not, and then you have to, yeah, you just have to check, but instead of printing it. So print list function gives away how you end up doing the search also. So this is all we have about linked list. So do you understand why this could be better than arrays? First question. We don't need to allocate memory, block memory a priori. You can keep going, going. Completely dynamic. This is a completely dynamic data structure. We don't need realloc, that's true. What could be a problem here? One more important thing, excellent thing, we can insert new element at any position without hassle. Yeah, awesome. So if you want to do insertion sort, very good. So let's say insertion sort. You have a so let's say initially you have let's say you are doing insertion sort using an array. Initially you see an element. You get an element 10, you get an element 20, and after that you see an element 15. If you see an element 15, so in order to insert it at the right position, you have to copy this this way, and you have to put in order to put in here. Or let's say the worst case, what is the worst case in insertion sort? So the worst case in insertion sort is, no, not the linked list. So if you are using an array to do insertion sort, so let's say you are inserting n numbers, you have initially number n, and then you see n minus 1. When you see n minus 1, so what you have to do is, no, you compare n minus 1 with n, and then you move here, and then you transform the list here. And then you want to insert n minus 2. When you want to move n minus 2 here, you figure out, n minus 2 is less than n, and then you copy, n2 here, and then you compare n minus 2 with n minus 1, and n minus 1 is also in the wrong position. You copy, and then you get n minus 2, n minus 1, n. And then you want to insert n minus 3 here, but you see that n minus 3 is out of place. You copy this here, and then you compare it with n minus 1. You copy it here, n minus 3, you compare it to n minus 2, you copy it here, and finally you get n minus 3, n minus 2, n minus 1, n. You understand what is happening? If you use an array, so you will end up doing lots of memcopy operations, copy operations, and the worst case time complexity turns out to be n square. But if you want to do insertion sort using a linked list, it becomes a relatively easy job if you want to do insertion sort using a linked list. Are you with me here? And what is one of the homework's problems? One of the homework problems is, how do you do insertion sort using linked list? No, you don't have, it will still be n square, but but in terms of the number of copy operations, it will be less. So is there any disadvantage with linked list when compared to arrays? Is there any traversing? So why is traversing problem in linked list? Karthik Lakshmanan says we lose the random access. Excellent. We lose random access of the array elements. We no longer can use indexing. That is one. And there is one more important thing. When we are iterating through the elements of an array, it is what is called as a regular memory access. So when you access A of 0, A of 1, A of 2, A of 3, like this, so this is what is called as a regular memory access. When there is regular memory access, when there is regular memory access, so cache utilization will be very good. So this leads to good cache utilization. But in a linked list, we do what is called as a pointer chasing. In linked lists, we do pointer chasing. So when we do pointer chasing, it's like in heap. So let's say if this is your heap of memory, so you start from here, you go here, from here you go here, and then you go here, and then maybe you go here. You are all over the place. So this is what is called as an irregular memory access. So when you have irregular memory access, you will have very bad cache utilization. So later on in your data structures course, you study a whole lot of data structures. Essentially, they are extensions of the idea that you have just seen now. Shashwat has this question, yeah, what is this bad cache utilization? So it requires a bit more. How big of it? What is a drawback? So this bad cache utilization is a real problem. It's a problem. So your performance of modern systems is seriously constrained by how fast you can access data from the memory. So if you're not able to use your cache well, then what happens is the performance will be seriously hit. So that is, does the cache gets freed after execution ends? Yeah, in a way, uh, but not exactly, yeah. But you can, for practical purposes, we can assume that the cache gets freed after execution. I'll just give a quick overview on why cache utilization is good in arrays. In arrays, let's say if you're scanning an array, you're scanning one byte after another byte. So when you're scanning one byte after another byte, the processor knows, or the cache controller knows, that you are going to access the next byte down the lane. And so it kind of prefetches that data for you, which makes, so by the time you actually touch a memory location, it is already present in the cache. But this doesn't kind of work in a heap, because in a heap, you access this element now, and later on you end up accessing this element, and then later on you end up accessing this element. Like that, you are all over the place. And because of that, the cache memory or the cache controller doesn't have any clue on what will be the next memory location you are going to access. Because of that, it cannot help you that much. But on the contrary, so that is irregular access is, it is hard for the cache controller to figure out what you are trying to do, and you lose out on it. Ha, Mugundan, that's a big question. So we should hold on to that. Yeah, it's a good question, but it's it's a different game. Uh, Kishore has a point. Kishore, there is something like that happens. There are what are called as prefetch instructions, and compilers try to do some stuff, but it is very hard job to do. If we do for I is equal to 0, I less than I, doesn't this become random for the processor to expect? No question that there is a periodicity. Now I is equal to I plus 3, the cache line prefetcher, it knows that you are doing what is called as a stride 3 access. Stride 3 means you are jumping by 3. So it will figure out that the stride of your memory access is 3, and it will do it. It will take care of it. All right. So what I would say is, I would like to stop the discussion on linked list here, because this is the basic idea. I want you to take a look at this code, and I would like you to work on the homework problems which I have given, which are based on this linked list idea. And if you are able to do the homework problems, then you will have a very good grasp of how these things work. It's already done, na? Awesome. Good, good. So, all right, I hope all of you are will be able to uh, take these ideas and be able to finish the homeworks on the homework problems related, which makes use of linked lists. Okay, so now I will quickly take 5 or 10 minutes to see if I can make little bit progress on the number representation and then leave you by 3-5. So yeah, let's. So here, what did you learn about number representation in your? Uh, what did you learn about number representation? Frame floating point numbers. It's very involved thing, so we will not talk about floating point representation. Maybe I can point to some resource. I'm sorry, but I hope you will get to learn it in your DSM course, or but I will point you to some resources. So you learned binary up to 2's complement. So why should we use 2's complement representation of numbers? What is 2's complement and why should we use 2's complement representation? No extra representation of subtract by adding. Make it easy to work with negative numbers. Good. So with this, I'll just give a quick recap. Let's say if you have bits, no, BW minus to B naught, this is a W bit number. So in unsigned representation, uh, so what is the value associated with it? Unsigned representation. So the value associated with it is sigma I is equal to 0 to W minus 1 2 power I into Vi. Are you with me here? This one? How we assign magnitude to this W bit binary number? Okay. So now in 2's complement representation, I'm using this TC. So B naught. So you have 2 power minus 2 power W minus 1. The most significant bit is what is called as a sign bit. This is what is called as a sign bit, the most significant bit. In 2's complement form, this has the magnitude minus 2 power W minus 1. And the rest you get is sigma I is equal to 0 to W minus 2, 2 power I Vi. Are you with me here on this 2's complement representation? Yeah, so let's say if you take 4-bit numbers, let's say if you're working with 4-bit numbers, so if you're working with 4-bit numbers, in unsigned representation, this is 2 power 0, this is 2 power 1, this is 2 square, this is 2 cube. But in 2's complement representation, so in 2's complement representation, this has value 2 power minus 3, 2 square, 2 power 1, 2 power 0. So if you take this 1001 and interpret it as a signed number, its value would be what? Its value would be minus 8 plus 1. This would be minus 7. But if you interpret it as an unsigned number, its value would be 8 plus 1. It is 9. Are you good here? This much? It is not minus 6, no? It is minus 7. Okay. So I hope you're all with me at least at this point. So one important thing that I want you to understand here is one beautiful thing about 2's complement representation of numbers is, or you can have a alternate representation which is called as a sign magnitude representation. In sign magnitude representation, you use this most significant bit. If it is equal to 1, you think of it as a negative number, and if it is equal to 0, you think of it as a positive number. So in sign magnitude representation, this will be equal to minus c. This is 2's complement representation. This is sign magnitude representation. This is unsigned representation. This you use it just as a sign bit. Okay. I hope you're all with me on this thing. So now, what is the beauty of 2's complement representation? The beauty of 2's complement representation is, if I ask you, hey, what is the sum of 1001, 0111? Then, so if I just give you these two 4-bit patterns, can you just go ahead and do arithmetic for me? Can you go ahead and do you need to ask me whether 1001 is a 2's complement numbers or unsigned numbers? Do you need to know? We don't need to know. This is the most important thing. Like for example, no, you know, there is so like for example, 1001. What is this? In unsigned representation, this is equal to 9 and 1, 2, 3. No, 1, 2, 4, 6. Right? So here, one of you could be working on this in this space. Like for example, Vivek could be interpreting this 1001 and 0110 as unsigned number, and I could be thinking of it, or someone else could be thinking of it as a 2's complement number or a signed number. So minus 7 plus 3. 1, 2 plus 4, 6. No? This is 6. Yeah, okay. Good. Sorry. This is 6. So this is what I would like to bring to your attention. This is minus 7 plus 6 is minus 1. And this is 1, 1, 1, 1. 9 plus 6 is 15. So the guy who is working in this space, he gets the right answer. And the guy who is working in this space, he also gets the right answer. But what we do in between is independent of whether we are coming from the left or we are coming from the right. How many of you are with me here? That is, whether we come from this to here or come from here. So it doesn't matter. The underlying arithmetic, the rules of binary arithmetic are exactly the same. Whether you come from this space, whether you are coming from this space, whether you are coming from this space, or whether you are coming from this space, it doesn't matter. What we do in the middle is exactly the same. So this has a phenomenal impact on the underlying processor design and underlying the compiler. It will have impact in many ways. So in order to understand this, are you all with me here? I hope you are with me, that whether we come from this world or this world, it doesn't matter. In the middle world, all you do is you just do regular binary arithmetic, and the guy who is coming from this world, he will move this way and get that the answer is minus 1, and the guy who is coming from this world, he will go this way and he will interpret the answer as 15. Yeah, exactly. Tanmay got it. Yeah. So you just have to choose a convention, and depending upon which side you are coming, you go back to that. Okay, so that's all it is. So this perspective, I really want you guys to think about it. This is a fantastic idea, that that whether you come from the one left or you come from the right doesn't matter. In the middle, the rules of binary arithmetic remains the same. Yes, that's true. 1, 1, all ones, when interpreted as a signed int, it is minus 1. So we are good. Minus 7 plus 6 is minus 1. Are you with me? I hope you are with me. Okay, so I want to show some code to drive this point further. Okay, hash include stdio.h int a b unsigned int ua ub float fa fb. Now let's say c is equal to a plus b, uc is equal to ua plus ub, and fc is equal to fa plus fb. Number.c. Did you see this code? Can you check this code? You're all good on this code. So we are not doing anything fancy here. GCC minus G number.c obj dump minus d minus s a dot out greater than one number dot dmp. Okay, so we are good here. Let's see, guys. Okay, you can see what I want you to pay attention is this. Okay, is the whole story is here. The whole story is, if you see, this is c is equal to a plus b. C is equal to a plus b, where a, b, c, these are signed integers. And the associated instruction to do the addition is add. And if you see UC is equal to UA plus UB, and if you see the associated instruction is only add. So whether you are adding unsigned numbers or signed numbers, it doesn't matter. We can use the same add instruction. That means you use the same add circuitry in the underlying processor, as long as you represent the numbers in the 2's complement form. As long as you represent signed numbers in the 2's complement form. And then, but if you see floating point numbers, fc is equal to fa plus b, so we have a different instruction for floating point numbers, because the arithmetic circuitry that needs to be invoked in your processor to perform floating point addition is different. So because of that, you generate a different instruction here. If you use sign magnitude representation to represent negative numbers or signed numbers, then you need to have a different add instruction to take care of signed numbers and unsigned numbers. Do you see the point here? Are you all with me here? This is a very important point. Just because we are representing numbers in 2's complement form, it is possible for us to get away with the same add instruction, which will invoke the same add circuitry. But if you are using sign magnitude representation, then the story doesn't work. You need to have a different circuitry or add algorithm to add sign magnitude numbers as against regular binary numbers. No, float doesn't use sign magnitude representation. It is a completely different representation. So because of that, we need to have a separate instruction to add floating point numbers, and the corresponding circuitry will be invoked. Make sense? I hope you are with me to some extent. If you're kind of bit lost, I'm really going fast because, last class I want to at least touch the topic for you. So if you're a bit lost, it's okay, don't worry. But one thing that I would like you to remember is when you are working with numbers, when you add two really large numbers, then things can go bad for you. When you add two really large numbers, you may end up getting a negative number, for example. Like for example, let's say a is equal to 0, E8, 085. What do you think if I add these two numbers, what do we get? If a is equal to, so on line number 9, if we do this addition, what do you get? C is equal to a plus b. This is how many? 20 bits, huh? So when you add these two numbers, what do you get? Is it a positive number, negative number? It's positive, huh? Still positive? No, I don't think so. 1, 2, 4, 8. It is, maybe I should use 1 to 4. Yeah, let's see what happens. Printf C is equal to %d C, this is C, numrep.c. Yeah, one easy way, of course, is, like I don't want this. What is the size of int? 4 bytes, right? So this is 1 byte, 2 bytes, fourth byte is all F, and 100. Maybe I'll use this. I don't want to use int max because I want to show when two positive numbers when two positive numbers are added, if you are not careful, so I just want to make this point, guys, okay, and then I leave it here. I want you to think about it. So this is what can happen when you are working with integers. When you are working with integers, as programmers, you need to be careful that when you add two large positive numbers, you may end up getting a negative number. This is because this is what is called as a overflow condition. And similarly, when you add two large negative numbers, and if you are not careful about this, you get into trouble in real life. You will get into, again, this is an underflow condition. Okay, underflow or whatever. So these are the two cases you need to worry. And if you add a positive number and a negative number, you're always good, because the number falls somewhere in between this. So because of that, you are good. Oh, that's only 6 hexaletters. Okay, got it. Yeah, now we have the fun. Yeah. Are you with me here? Because the actual arithmetic that happens in practice is modular arithmetic. And so similarly, when you are working with unsigned numbers, like for example, let's take these unsigned numbers. You add two really large numbers. What do you think will be the sum of? So what will be the sum of UA and UB? What will be the sum of UA and UB? Let's see. 1, 2, 3, 4. Oh, I didn't do this addition. UC is equal to UA plus UB. Huh, I got -2. Huh? I don't know why I'm getting -2. Anyway, so if some of you are a bit lost here, it's okay, guys. I'm just going too fast in this class. Yeah, warning, it's okay, don't worry. Why is there a E for UC? There should not be an E, no? 1, 2, 3, 4. Oh, okay. The percent U also shouldn't matter, because you're supposed to get a 0 when we add these two. 2, 3, 4. Yeah, something is happening. So, but in any case, the point I want to make here to conclude this lecture. Yeah, so let's not worry about all these things. I just want to make few points. What are the important points about representation of signed and unsigned numbers? Oh, why 0? Krishna Pranit has a good question. Oh, some thought process was there. Okay. So anyway, I want to conclude this lecture, because some of you may be a bit lost because we are doing a bit fast, but I want to summarize what we discussed so far. Number one is 2's complement representation of numbers is very fantastic thing, because whether we kind of no use in the underlying system, it doesn't know whether you are working with 2's complement numbers or unsigned numbers, because the rules of the binary arithmetic remains the same underneath. So because of that, what happened is this instruction, in order to take care of this computation, we are using the same add. This is the first point of today's lecture. And this is only possible because we are representing signed numbers using 2's complement representation. Okay, are you with me here? This is the first point. The second point is, uh, see, remember these integers, signed integers or unsigned integers, they are allocated 32 bits. So when you add two large unsigned numbers, what can happen is the result may not fit into 32 bits, and because of that, overflow happens. Like for example, so like if you are working with, if you are given only 3 bits to represent, you can represent 0 to 7, right? So what happens is if you do 2 plus 3, you get 5, not a problem. But if you do 3 plus 5, you will get 8. So 8 is nothing but 100, and this is an overflow bit, and you get only these 3 zeros, and you say, the result that you obtained is zeros. So this is the overflow condition. And you have to be careful when you are working with numbers, because when there is an overflow, you don't get any kind of error. Like for example, you may have tested your program using small numbers, but in production you got big numbers, and you get into this kind of problems. So by default, we use two's complement. C compiler uses two's complement convention. Pretty much all systems that you see, they use two's complement convention. So you need to pay attention when you are working with numbers because of these overflow conditions. And if you add two positive numbers, if the two positive numbers are really large, you may end up getting a negative number. And if you add two large negative numbers, you may end up getting an overflow or underflow. Again, you may end up getting a positive number. And if you add a positive number and a negative number, you don't get into trouble. So these things you need to keep in memory, because if you don't know these things, then what will happen is you will end up making mistakes. So you will end up in your programs, and that could be some serious programs down the lane. So that is what, that's the reason for this. And you will read these things in your CSO course, hopefully. At that time, a greater clarity on this will emerge. And I will also post a handout on our course website so that you can read it a bit and get a better understanding. So with that, I conclude today's lecture. I am a bit sorry that we went fast in the last half an hour especially, but it is okay. You will learn in a later class in a greater depth. I will commit this code, and so yeah, as I said, today is the last lecture, and thank you all for being fantastic students, and I enjoyed your company through this whole semester. I miss out on those students who are not who couldn't express themselves here on this chat, because I really would love to know each one of you and see what went well for you, what went no, didn't go well with you, and how I can help you to to get things better for you. So I feel for all those of you who are who couldn't talk on this chat. So good. We'll catch up again. So after, yeah, I really look forward to meeting all of you when you all physically in the campus. Yeah, we'll definitely, we should all meet up after you join. Yeah, I teach compilers and CSO I used to teach earlier, but now I'm not teaching CSO. So that's good, guys. So again, sorry. Yeah, we'll have a treat. We should have a proper meet and treat once we all come together and